Okay, let's start by focusing the problem. And what I show is a picture of the car driven by Bonnie and Clyde. It's moving at 108 kilometers per hour, and the cop car moving at 2 meters per second. Now, what is the fundamental question that we're asking? We're asking whether or not the cop will catch up to Bonnie and Clyde before reaching the state line. Another way to phrase that question is, at what distance does the cop catch up to Bonnie and Clyde? Now we have to think about how we're going to approach this problem. So our approach, since Bonnie and Clyde and the cop all start together, we've got to think that both will of course be at the same distance when the cop catches up to Bonnie and Clyde. My first goal is to describe the physics. And if you'll look right here, we have the object Bonnie and Clyde moving at velocity bc. We have a cop moving with acceleration a. We show that at time xc/tc that the cop has caught up with Bonnie and Clyde. And we don't know where this xc and tc is going to occur. I'm putting it in here because I think it's going to occur in here, but it could very well occur out here. And we define our quantities: x0 as the start position, t0 the start time, xc the position of catch-up, tc the time of catch-up, xl is the position of the state line, and we have vbc, the velocity of Bonnie and Clyde, a is the acceleration of the cop, and we know this is 108 kilometers per hour, and this is 2 kilometers per hour. The target quantity of interest is xc. Where does the cop catch up to Bonnie and Clyde? And we have the following quantitative relationships. xbc, which is the position of Bonnie and Clyde, is equal to the velocity of Bonnie and Clyde times the time, and the position of the cop is equal to 1/2 times the acceleration times the change in time. And where I have taken the initial position of each one to be 0. Our first goal is now to plan the solution. So I'm going to use the two equations that we had previously. One, I'm going to set xc, the position of catch-up, equal to the velocity of the Bonnie and Clyde times the change in time from t0 to tc. Doing that, I'm going to solve for tc minus t0. Then I'm also know that the cop in time tc minus t0 also goes xc, according to 1/2 a times the change in time squared. Now I already have the change in time up here, so I'm just going to substitute down here the change in time, and I get the equation below, relating the position of catch-up to the position of catch-up squared times the acceleration. Solving for the position of catch-up, I get the final equation here. Now, what about units? Well, remember we were given that the velocity of bc, the Bonnie and Clyde, is 108 kilometers per hour, and the acceleration is 2 meters per second squared. So I'm going to convert 108 kilometers per hour to 30 meters per second. Executing the plan, I come up here and I plug in my numbers. 2 times 30 meters per second squared over 2 is equal to 900 meters. I find out that the cop catches up to Bonnie and Clyde in 900 meters. And finally, I evaluate the solution. Is the answer properly stated? Yes, it states what distance the cop catches up. Is it unreasonable? No. And is the answer complete? Yes, that is all the information that I required.